Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into something that feels incredibly familiar, and yet quietly mysterious. We're going to explore what a photon really is, but before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable, and when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a gentle reminder of how many different lives are softly intersecting in this shared moment. Now feel free to dim the lights, maybe let a soft breeze or a fan hum quietly in the background, and allow your body to relax. There's nothing to solve tonight. Nothing to figure out all at once, just something to slowly drift through, like watching ripples spread across still water. Because the thing we're about to explore, light, is something you already know, or at least something that feels like you should. And yet, the deeper we look, the less certain it becomes. So let's begin gently with something simple. There is a quiet kind of presence that follows you through almost every moment of your life. It rests on your skin when you step outside. It fills your room when you turn on a lamp. It glows softly from the screen in front of you right now. You don't usually think about it. It's just there. Light. It feels so natural that it almost disappears into the background of existence. You wake up and the world is visible. You walk through your day and everything has shape, colour, distance. You look at a tree and without effort, you understand where it begins and ends. You look at a face and you recognise it instantly. All of this quietly and invisibly depends on light. And yet, if you pause for just a moment and ask a very simple question, what is light actually? The answer is not nearly as simple as it seems. For something so familiar, light carries a strange collection of properties that don't quite fit together the way you might expect. For example, light has no weight. You could not hold a piece of light in your hand even if you tried. It has no mass, no substance in the way a stone or a drop of water does, and yet it carries energy. Enough energy, in fact, to warm your skin when sunlight reaches you after travelling across space, enough to power solar panels, enough to drive the chemistry of life itself through photosynthesis. So here is the first quiet contradiction. Something that has no mass still carries energy across the universe, and that energy moves at a very specific speed. Not just fast, but incredibly precise. About 300,000 kilometers every second, fast enough to circle the Earth many times in the blink of an eye, fast enough that for most of human history it might as well have been instant. But even this is only the beginning, because there is something even stranger hidden beneath that speed. If you imagine a beam of light travelling from the surface of the sun to your face, you might picture it moving across space over several minutes. And from your perspective, that is exactly what happens. It takes a little over 8 minutes for sunlight to reach Earth. But from the point of view of the light itself, that journey does not unfold the same way. In fact, in a very real sense, it does not unfold at all. For light, there is no passage of time between the moment it leaves the sun and the moment it reaches you. No waiting, no travelling, just arrival. It is as if the entire journey, across millions of kilometers, is compressed into a single, timeless instant. Now, you don't need to fully understand that yet. It's something we'll return to slowly, later on. For now, it's enough to let the idea rest quietly in the background. Because there's another strange feature of light that is perhaps even more unsettling. Sometimes light behaves like a wave. Imagine dropping a small stone into a still pond. Ripples spread outward in smooth, overlapping circles. They interfere with each other, creating patterns of peaks and valleys. Light can do something very similar. It can spread out, overlap, and form patterns that only waves can create. But at other times, light behaves like something entirely different. It behaves like a particle, like a tiny localized event, a single point of interaction, a small packet of energy arriving at a specific place. And here is the part that makes physicists pause. It is not that light is sometimes a wave and sometimes a particle in a simple, predictable way. It is that the way light behaves seems to depend on how you choose to observe it. If you look for waves, you find waves. If you look for particles, you find particles. It is as if light is not fully committed to being one thing or the other until it is asked. And even that phrasing might not be quite right. Because as we will slowly discover, light is not really a wave in the way water is a wave. And it is not really a particle in the way a grain of sand is a particle. It is something else. Something that doesn't quite fit into the categories our intuition is comfortable with. Something that has forced physicists over and over again to rethink what it means for something to exist at all. And at the heart of all of this is a single idea, the photon, not a tiny ball of light, not a little object flying through space, but something more subtle, something closer to an event than a thing, a moment where energy appears, travels, and disappears again, leaving behind only its effect. If that sounds a little abstract, that's perfectly fine. You don't need to hold all of it at once. For now, just let the strangeness settle in gently. Light is everywhere. It allows you to see. It carries energy across unimaginable distances. It moves at the fastest speed the universe allows. It behaves like a wave and like a particle, and somehow neither at the same time. And despite all of this, it feels completely ordinary. That quiet tension between the familiar and the deeply strange is what makes the story of light so fascinating. Because the more carefully we look at it, the more it begins to slip away from our expectations. And as we continue, we'll slowly trace how humanity tried to understand this simple, everyday phenomenon, and how, step by step, that understanding led us into one of the strangest corners of reality, where even something as gentle as light begins to feel like a mystery. If you sit quietly with the idea of light for a moment, something begins to feel slightly out of place, not in a dramatic or obvious way, but in a subtle, almost whisper-like way, as if the concept itself doesn't quite settle into the shapes your mind expects. When we think about particles in everyday life, we imagine small, solid things, a grain of sand resting on your fingertip, a drop of rain sliding down a window. Even something as tiny as dust floating in the air still feels like it exists in a definite place, at a definite moment. Particles, in the way we usually understand them, are things you could point to, things that have a location, things that move along a path. If you throw a small ball across a room, you can imagine its journey. It starts in your hand, travels through the air, and lands somewhere else. At every moment along the way, it has a position. Even if you don't track it precisely, it feels continuous, predictable, grounded. And so, when scientists began describing light as being made of particles, what we now call photons, it seemed at first like a return to something familiar, a comforting idea. Light is a stream of tiny invisible pellets, each carrying a little bit of energy. But the more carefully we look, the more that picture begins to dissolve, because a photon does not behave like a tiny ball. It doesn't travel along a neat, well-defined path from one place to another. It doesn't quietly exist in a specific location as it moves through space. And perhaps most surprisingly of all, it doesn't seem to have a clear identity between the moment it is created and the moment it is detected. To understand this, it helps to imagine not an object but an interaction. Picture a quiet room. somewhere on one side of the room a small event happens, a tiny release of energy, and somewhere else, perhaps on the opposite wall, that energy is absorbed. Between those two moments, release and absorption, we often imagine something travelling, a small object crossing the space between them. But with a photon, that image becomes difficult to hold on to. In many experiments, when scientists try to trace the path of a photon, they find that it doesn't behave as though it followed a single well-defined route. Instead, it behaves as if it explored many possibilities at once, only settling into a definite outcome when it finally interacts with something. It's almost as if the photon is not a traveller moving through space in the usual sense, but a connection between two events, a beginning and an ending, an emission and an absorption. And what exists in between is not a tiny object with a clear trajectory, but something more like a spread of possibilities, quietly unfolding in ways that resist simple description. If that sounds abstract, you can think of it like a faint echo in a large hall. You don't see a solid object moving from wall to wall. Instead, you experience a pattern that seems to exist across the entire space until it finally resolves into a sound reaching your ear. In a similar way, the photon does not appear to be in one place at one time in the way we expect. It is described not as a point, but as a range of possible outcomes, each with its own likelihood. And when the interaction finally happens, when the photon is detected, it doesn't arrive gradually. It appears all at once, a single, discrete event, a tiny packet of energy delivered in full. This is where the particle-like nature of the photon becomes clear. No matter how gently or gradually you try to observe light, it is always absorbed in these indivisible chunks. It never arrives as half a photon or a fraction of one. It is always whole, and yet everything leading up to that moment does not resemble the motion of a classical particle at all. There is another quiet detail that adds to this strange picture. Even though photons have no mass, they still carry momentum. That means they can exert a small push when they interact with matter. Not a strong push, like a gust of wind or a flowing current, but something incredibly gentle. So gentle that you would never notice it in daily life. And yet, in the vacuum of space, where there is no air resistance and no friction, even that tiny push can have an effect. Engineers have imagined and even begun to test the idea of spacecraft that move not by burning fuel, but by catching light itself. Thin, reflective sails spread out like delicate wings, pushed ever so slightly by the steady stream of photons coming from the sun. Over time, that gentle pressure adds up, a slow, quiet acceleration, driven by something that has no mass at all. This is another reminder that the photon does not fit neatly into the categories we are used to. It behaves like a particle when it delivers energy in a single event. It behaves like a wave when it spreads out and interferes, and in some ways, it behaves like neither. It is something that challenges the very idea of what a thing is, because if something has no mass, no definite position, no continuous path, can we still call it an object? Or is it more accurate to think of it as a process, a happening, a brief structured transfer of energy from one part of the universe to another? This shift, from thinking of photons as objects to thinking of them as events, may feel subtle, but it opens the door to a very different way of understanding reality. Instead of a world made of tiny building blocks, neatly arranged and moving along predictable paths, we begin to glimpse a world where interactions come first, where what matters is not what something is, but what it does. A world where existence is less about static things and more about relationships unfolding over time. And perhaps that is why the photon feels so elusive, because it sits right at the boundary between our everyday intuition and a deeper, more fluid description of reality, a place where the familiar idea of a particle begins to soften and something more subtle takes its place. As we continue, we'll gently step back into the long human story of trying to understand light, how for centuries people tried to fit it into simple categories, and how, again and again, those categories quietly fell apart. If you travel far enough back in time, long before telescopes, long before laboratories, and long before the quiet precision of modern science, you find a world that feels both familiar and strangely different. People still woke up to sunlight. They still watched shadows stretch across the ground. They still saw reflections in water and wondered, perhaps briefly, why the world appeared the way it did. But when they asked the question, how do we see? The answers they imagined followed a very different path. One of the earliest ideas proposed by thinkers like Plato suggested something that might feel unusual to us now, but at the time seemed quite natural. They believed that vision worked because something came out of the eyes. In this view, the eyes were not passive receivers, but active emitters, a kind of gentle beam or invisible fire extended outward from the eyes, touching the objects around us. And when this invisible stream reached something, it allowed us to perceive it. It's a quiet, almost poetic idea, that seeing is not something that happens to you, but something you reach out and do. If you think about it for a moment, it even feels intuitive in a certain way. When you look at something, it can feel as though your attention is moving outward, connecting with the object, as though your awareness is stretching across space. And so, for a long time, this idea held a certain appeal. But not everyone agreed. Another line of thought associated with Aristotle imagined something quite different. Instead of light coming from the eyes, it suggested that the world itself contained a kind of medium, something like a subtle substance filling space, and that changes in this medium allowed us to see. In this picture, light was not a stream from the observer, but something happening in the environment, a disturbance perhaps that travelled through space and reached the eye. It was closer in spirit to the idea of waves moving through water. Even at this early stage, you can feel the beginnings of a pattern that will repeat itself again and again throughout the history of light. Two competing intuitions, one that treats light as something like a particle, travelling in straight lines, another that treats it as something like a wave spreading through a medium, and for a long time there was no clear way to decide between them. The world simply looked the way it looked, and human intuition, shaped by everyday experience, filled in the rest. But as centuries passed, a quiet shift began to take place. Careful observation started to replace pure speculation. And one of the most important figures in that transition was a scientist working many centuries later in a very different part of the world. His name was Ibn al-Haytham. Instead of relying on intuition alone, he began to test ideas about light with experiments, simple, careful setups that allowed him to isolate what was actually happening. One of his key insights was surprisingly straightforward. Light does not come from the eyes, it enters them. If you open your eyes in a dark room, you see nothing. But when light from an external source, like the sun or a lamp, reaches your eyes, vision becomes possible. This might seem obvious now, but at the time it represented a profound shift. Seeing was no longer an active projection outward, it was a reception, something from the world arriving at you. And once that idea took hold, it began to reshape how people thought about light itself. If light travels into the eye, then it must move through space. And if it moves through space, then perhaps it has a direction, a speed, and a structure that can be studied. Suddenly, light was no longer just a philosophical idea. It was something that could be investigated, measured, understood. This change marked the beginning of optics as a true scientific field. But even with this progress, the deeper question remained unanswered. What is light actually made of? Is it a stream of tiny particles moving in straight lines from source to observer? Or is it a wave-like disturbance spreading through space? Or is it something else entirely? At this point in history, there was still no clear answer, and perhaps more importantly, there was no strong reason to abandon either idea completely, because both seemed to explain parts of what people observed. Light travels in straight lines, casting sharp shadows, something that feels very particle-like, and yet it can also bend slightly around obstacles and spread in ways that feel more like waves. It was as if light was quietly refusing to fit into a single category. And so the question lingered, unresolved, waiting for a new kind of insight, a new way of looking. As we move forward, we'll see how this tension slowly builds, how different thinkers tried to capture light within familiar ideas, and how each time something subtle slipped through the cracks. Because the deeper we follow this story, the more it begins to feel like light is not just something we observe, but something that gently challenges the way we think itself. And in that sense, this early confusion is not a mistake. It is the beginning of a much longer journey, one that will eventually lead us to question not just what light is, but what it means for anything to exist at all. As the idea slowly settled that light enters the eye rather than emerging from it, something quiet but profound began to change in how people understood the world. Seeing was no longer an act of reaching outward, it became an act of receiving. And with that shift, a new question naturally followed. If light comes from the world and reaches us, how does it travel? It's a simple question on the surface, but it carries with it a deep curiosity. Because once you begin to imagine light as something moving through space, you can no longer think of it as just a passive condition of visibility. It becomes something active, something dynamic, something that unfolds between objects and observers. To explore this, early scientists began to notice patterns, small, consistent clues that hinted at the nature of light's motion. One of the clearest was something you've likely seen many times without giving it much thought: shadows. If you place an object in front of a light source, the shadow it casts is often sharp and well defined. The edges are clear. The shape closely matches the object itself. This suggests something important. Light seems to travel in straight lines. If it didn't, if it curved or spread too freely, the edges of shadows would blur significantly. Instead, they maintain a kind of crispness, as though light is moving along direct paths, like invisible threads stretching from the source to the surface. You can imagine it almost like rain falling in straight lines from the sky. If something blocks the rain, the ground behind it stays dry in a matching shape. Light behaves in a similar way. This observation led many thinkers to lean toward the idea that light might be made of particles, tiny entities moving along straight trajectories, like countless microscopic projectiles. And yet, even at this stage, there were hints that the story might not be so simple. Because under certain conditions, light does not behave quite so neatly. If you narrow a beam of light enough, passing it through a very small opening, for example, it begins to spread out slightly as it emerges. The sharpness softens, the edges blur. It's subtle and easy to overlook, but it suggests that light can bend just a little around obstacles, and that behavior feels less like particles and more like waves. This quiet tension continued to build as observations accumulated. Another clue came from reflection. When light strikes a smooth surface, like a mirror, it reflects in a very predictable way. The angle at which it arrives matches the angle at which it leaves, creating the familiar behavior we rely on every day. This regularity reinforced the idea that light follows consistent paths. But then there was refraction. the bending of light as it passes from one medium to another, like from air into water. If you've ever looked at a straw in a glass of water, you may have noticed that it appears slightly bent at the surface. This is not because the straw itself changes shape, but because the light travelling from the submerged portion to your eyes changes direction along the way. It slows down slightly as it moves through water, and that change in speed causes its path to shift. Even without using equations or technical language, you can imagine this as a kind of hesitation, a subtle adjustment in the journey of light as it passes through different environments. And once again, we see a pattern emerging. Light behaves in ways that are structured and predictable, but not always simple. It moves in straight lines but can also bend. It creates sharp shadows, but can also soften and spread. It reflects cleanly, but also refracts in ways that depend on the medium it passes through. All of these behaviours could be described, measured, and even predicted with increasing accuracy. But the deeper question remained untouched. What is light actually made of? Is it composed of tiny particles moving along invisible paths? Or is it a kind of wave travelling through space, like ripples across a pond? At this point in history, the answer was still unclear, but something important had changed. The focus had shifted from abstract speculation to careful observation. Instead of asking what light should be, scientists began asking what light actually does. And that shift, from imagination to experimentation, would eventually lead to one of the most important breakthroughs in our understanding of the universe. Because as these observations became more precise, they began to reveal patterns that pointed toward a unifying idea. A way to connect electricity, magnetism, and light into a single, elegant framework. An idea that would suggest that light is not made of particles at all, but is instead a kind of wave travelling through space itself. For a moment it would seem like the mystery of light had finally been solved, but as we'll gently discover, that clarity would not last. Because just as the wave picture of light became more complete, small cracks would begin to appear, and through those cracks, a deeper and far stranger reality would slowly come into view. As observations about light became more careful and consistent, a quiet tension began to sharpen into something clearer. Light behaved in structured, predictable ways. It moved in straight lines, reflected cleanly, and bent when passing through different materials. These patterns invited explanation, not just description, but a deeper understanding of what light is. And so, in the 17th century, two very different ways of thinking about light emerged, each guided by intuition, each supported by evidence, and each, in its own way, incomplete. On one side was Isaac Newton. Newton imagined light as a stream of tiny particles, not objects you could see, of course, but incredibly small entities, moving rapidly in straight lines. In his view, when a light source emitted light, it was releasing countless minute particles that travelled outward and interacted with the world. This idea fit naturally with several observations. The sharpness of shadows, for instance, made sense if light consisted of particles moving in straight paths. Just as a wall blocks a stream of tiny projectiles, an object blocks these light particles, creating a clearly defined shadow behind it. Reflection also aligned well with this picture. If light particles struck a surface, they could bounce off in predictable directions, much like small balls rebounding from a wall. The angle of approach matching the angle of departure felt intuitive within this framework. Even refraction, the bending of light as it passes from air into water or glass, could be explained. Newton suggested that light particles might speed up or slow down depending on the material, causing their paths to bend slightly as they crossed boundaries. Altogether, the particle model offered a coherent, almost comforting image. Light as a stream of tiny travellers, each following a path, each behaving according to familiar rules. But on the other side stood Christian Huygens, who saw something different. Huygens imagined light not as particles, but as a wave. In his view, light spread out from its source the way ripples spread across the surface of water. Each point on a wavefront could be thought of as generating new waves, creating continuous, expanding pattern. This idea too matched certain observations. The slight bending of light around small openings, the soft spreading that occurs when light passes through a narrow slit, felt much more natural in a wave picture. Waves, after all, can flow around obstacles and interfere with each other in ways that particles cannot. Refraction also took on a new meaning. Instead of particles changing speed individually, the wave itself changed speed as it moved through different materials, causing its direction to shift. You can imagine this like a line of people walking together, where one side enters soft sand while the other remains on firm ground. The difference in speed causes the entire line to pivot slightly. This wave-based explanation offered a different kind of elegance. Instead of countless individual particles, light became a unified motion, a continuous disturbance travelling through space. And yet, despite their differences, both models seem to capture something real. The particle model explained the straight-line motion of light and the clarity of shadows. The wave model explained bending, spreading, and subtle interference effects. It was as if light was revealing two different faces depending on how you looked at it, and for a time, the debate remained unresolved. Supporters of Newton's view pointed to the precision and clarity of his explanations. Supporters of Huygens' view pointed to phenomena that seemed difficult to reconcile with particles alone. There was no decisive experiment yet, no single observation that could clearly favour one model over the other. So the two ideas coexisted, each gaining support, each facing challenges. If you imagine standing in that moment without the benefit of modern knowledge, it might feel like trying to describe something just beyond your reach. Something that almost fits into familiar categories but not quite. You might lean toward one explanation, then encounter an observation that gently pulls you toward the other, back and forth, particle or wave, object or motion, and perhaps even then there was a quiet sense that the answer might not lie entirely within either framework. That light might not be fully captured by the concepts available at the time, but science often moves forward not by immediate clarity, but by accumulating tension, by allowing contradictions to persist long enough that a deeper understanding becomes necessary. And that moment was approaching, because soon an experiment would be performed, simple in design, almost delicate in its execution, that would seem to tip the balance decisively. An experiment that would make light behave unmistakably like a wave. For a while, it would feel like the question had finally been answered, but as we will slowly discover, that answer would only open the door to an even deeper mystery. One that would eventually lead us to question not just the nature of light, but the nature of reality itself. There are moments in the history of science that feel almost quiet when they happen. No sudden noise, no dramatic shift in the sky. Just a simple setup, a careful observation, and a result that gently changes everything. One of those moments came with an experiment that, at first glance, looks almost delicate. A beam of light, a thin barrier, and two narrow openings placed side by side. This is the experiment often associated with Thomas Young, and for a time it seemed to provide a clear and final answer to the question that had lingered for so long. Is light a particle or a wave? To understand what happens, it helps to imagine the setup slowly, as if you were building it yourself. You begin with a source of light, perhaps a soft, steady beam shining forward in a darkened room. In front of that beam, you place a barrier with two very thin slits cut into it. Behind the barrier, you place a screen where the light can land. Now, if light were made of particles, tiny individual projectiles, you might expect something simple. Each particle travels in a straight line. Some pass through the left slit, others pass through the right. When they reach the screen, they form two bright regions aligned with the slits, two openings, two clusters of light, clean, direct, predictable. But that is not what happens. Instead, something far more subtle appears. On the screen, rather than just two bright bands, you begin to see a pattern of alternating light and dark stripes, a series of gentle, repeating lines spreading outward from the centre. Bright, dark, bright, dark, like ripples overlapping on the surface of a quiet pond. This pattern is known as an interference pattern, and it carries a very specific meaning. It tells you that light is not simply arriving as independent particles, it is behaving like a wave. To see why, imagine again dropping two small stones into still water side by side. Each stone creates its own set of ripples, spreading outward in circles. As those ripples expand, they begin to overlap. In some places, the peaks of one ripple meet the peaks of another, creating a slightly larger wave. In other places, a peak meets a trough, and they cancel each other out, leaving the surface nearly still. The result is a pattern, alternating regions of reinforcement and cancellation. That is exactly what appears in the double-slit experiment. Light, passing through both slits, behaves as if it spreads out, overlaps with itself, and creates regions where it strengthens and regions where it fades. This is not something particles, in the classical sense, are expected to do. Particles do not interfere with each other in this way. Waves do. And so, for a time, this experiment seemed to settle the debate. Light is a wave, not a stream of tiny objects, but a continuous motion, spreading through space, capable of overlapping and interfering with itself. It was a beautiful result, elegant, convincing, almost final. And for many years, this wave picture of light became widely accepted. It fit naturally with other discoveries, especially as scientists began to understand electricity and magnetism as interconnected phenomena. Light, it seemed, was part of a larger story, a wave travelling through the fabric of space itself. But as often happens in science, clarity can be temporary, because hidden within this very experiment, within the same simple setup of slits and screen, was a deeper mystery waiting to be uncovered. At first, the experiment was performed with a steady beam of light, many photons flowing together. The resulting pattern looked smooth and continuous, like a soft wash of brightness across the screen. But then, someone asked a quieter, more delicate question. What happens if you reduce the intensity of the light? Not just dimming it, but lowering it until only a single photon passes through the slits at a time. Imagine that. Not a continuous beam, but individual isolated events. One photon, then another, each separated in time like distant raindrops falling one by one. If light were purely a wave, you might expect that reducing its intensity would simply make the pattern fainter. If it were purely a particle, you might expect that each photon would pass through one slit or the other, landing somewhere behind it, gradually building up two clusters. But what actually happens is far more intriguing. At first, as each photon arrives, it appears as a tiny localized point on the screen, a single dot, a small discrete event. It looks exactly like a particle. But as more and more of these individual dots accumulate, something remarkable begins to emerge. The same interference pattern, the same alternating stripes of light and dark, slowly, patiently, built up one photon at a time. It is as if each photon, arriving individually, somehow contributes to a pattern that requires wave-like behavior. as if each one is not just passing through one slit, but, in some sense, exploring both. And yet, when it is finally detected, it appears in one place, as a single event. This is the moment where the story begins to shift again, because now it is no longer enough to say that light is a wave, nor is it enough to return to the idea that it is a particle. It seems to be both, and neither. A single photon behaves like a particle when it arrives, but like a wave when it travels. And even that description feels incomplete, because it suggests that the photon switches between two modes, when in fact it may be something that does not fit into either category at all, something that only reveals certain aspects of itself depending on how we look. This experiment, simple as it is, does not just answer a question, it opens a new one, and from this point forward, the nature of light becomes something far more subtle, far more elusive, and far more deeply connected to the nature of reality itself. As the debate between particles and waves continued quietly in the background, something remarkable began to unfold in another part of physics. It did not begin with light at all. Instead, it began with two phenomena that, at first glance, seemed separate: electricity and magnetism. You can imagine electricity as something familiar. The gentle flow that powers your home, the small spark when you touch a metal surface after walking across a carpet, the steady current that charges your devices. Magnetism feels different, but equally familiar. The invisible pull of a magnet, the way a compass needle turns to align itself with the earth, the quiet force that seems to reach through space without touching anything at all. For a long time, these two forces were studied separately, but gradually, scientists began to notice that they were not as independent as they appeared. A moving electric charge could create a magnetic effect, and a changing magnetic field could in turn create an electric effect. It was as if the two were quietly intertwined, each capable of giving rise to the other. This relationship, subtle at first, was brought together into a single, unified picture by James Clerk, Maxwell. Maxwell did something extraordinary. He described electricity and magnetism not as separate forces, but as different aspects of a single connected system, what we now call the electromagnetic field. You can think of this field not as a physical substance you can touch, but as something that exists everywhere, quietly present even in empty space. A kind of invisible structure that can carry energy and change over time. Maxwell's insight was that when this field changes, it can sustain a kind of self-propagating motion. An electric change creates a magnetic change. That magnetic change creates a new electric change, and so on, back and forth in a continuous rhythm. Like a pair of dancers, each movement giving rise to the next. This self-sustaining pattern can travel through space, not because something is pushing it forward, but because it continually recreates itself, step by step, as it moves. A ripple, but not in water. A ripple in the electromagnetic field itself. And when Maxwell carefully worked through the implications of this idea, he found something astonishing. These ripples should move at a very specific speed, a speed determined not by the properties of any material, but by the fundamental nature of the field itself. When he calculated that speed, it matched something already known: the speed of light. This was the moment where everything seemed to come together. Light is an electromagnetic wave, not a stream of particles, not a mysterious emission, but a natural oscillation of the electromagnetic field travelling through space at a constant speed. It was a deeply satisfying answer, elegant, unified, almost inevitable, once seen clearly. And it carried with it another important implication. If light is a wave in the electromagnetic field, then it does not need a material medium to travel through. Earlier ideas had suggested that waves required something to move within, like water or air. There had even been speculation about a subtle, invisible substance filling space, sometimes called an ether, that would carry light waves. But Maxwell's theory made that unnecessary. The field itself was enough. Space was not empty in the way people once imagined. It was capable of supporting these gentle, travelling oscillations. Light didn't need a substance to move through. It was a motion of the structure of space itself. This realization expanded the meaning of light even further. It was no longer a special case, something unique and separate. It became part of a broader family, a continuous spectrum of electromagnetic waves, ranging from long, slow waves that we now associate with radio signals to shorter, more energetic waves like visible light, and beyond. You can imagine this spectrum like a long, seamless scale. At one end, waves stretch out gently, with long distances between their peaks. At the other, they become tightly packed, with rapid oscillations. Visible light occupies just a small portion of this range, a narrow band that our eyes are sensitive to. Beyond that, there are many forms of light we cannot see, but which behave in similar ways. All of them, according to Maxwell's picture, are expressions of the same underlying field. For a moment in history, this felt like a kind of completion. The question of light, debated for centuries, seemed to have found its answer. It is a wave, a beautiful, self-sustaining oscillation in an invisible field that fills the universe. And with that answer came a sense of calm, a feeling that the pieces had finally fallen into place. But as we've quietly learned to expect, such moments of clarity can carry within them the seeds of future questions. Because even as Maxwell's theory succeeded in describing how light behaves on large scales, small details began to emerge that did not quite fit. At first, these details were easy to overlook, tiny inconsistencies, subtle mismatches between prediction and observation. But over time, they began to grow, and eventually they would lead to a realization that this elegant wave picture, as beautiful as it was, could not be the full story. That something deeper and far stranger was waiting just beneath the surface. For a while, Maxwell's picture of light as a wave brought a quiet sense of completeness. It felt as though something fundamental had finally been understood. Light was no longer mysterious in the same way. It had a place, a role, a structure within a broader framework that connected electricity, magnetism, and motion. It was elegant, and perhaps because of that elegance it was easy to trust. But science has a way of gently testing even its most beautiful ideas, not by dramatic contradiction at first, but through small, persistent questions. And one of those questions began with something very ordinary: heat. Imagine holding a piece of metal over a flame. At first, it warms slowly, invisible to the eye. Then, as the temperature rises, it begins to glow faintly. A soft red, barely noticeable in a bright room. If you continue heating it, the colour changes, from red to orange, from orange to a soft yellow, and eventually, if the heat is intense enough, to a pale white glow. This gradual shift in colour is something you may have seen in everyday life, perhaps in a kitchen stove, a filament bulb, or even a campfire where embers glow brighter as they heat up. At the time, scientists were deeply interested in understanding this process. What determines the colour of heated objects? Why does increasing temperature change the light that is emitted? And most importantly, could this behaviour be predicted precisely? To explore this, they began studying what is known as a black body, an idealised object that absorbs all incoming energy and re-emits it as radiation. You can think of it as a perfect emitter, one that reflects nothing, and instead transforms all absorbed energy into light. It's a simplified model, but a very useful one. By studying how a black body emits light at different temperatures, scientists hope to uncover a deeper pattern, a universal rule governing the relationship between heat and radiation. At first, everything seemed manageable. Classical physics, using the wave description of light, provided a way to calculate how energy should be distributed across different types of waves. Longer waves, shorter waves, everything should follow a predictable curve. But when those predictions were compared to actual observations, something unsettling appeared. The theory worked well for longer wavelengths, those associated with lower energy radiation, like the gentle warmth you feel without seeing. But as the wavelengths became shorter, corresponding to higher energy light, the predictions began to drift, and then, quite suddenly, they broke down completely. According to the classical equations, as the wavelength became shorter and shorter, the amount of energy emitted should increase without limit. Not just increase a little, increase endlessly, an infinite amount of energy pouring out at the shortest wavelengths. You don't need to follow the mathematics to sense that something is wrong here. If this were true, any heated object should release an overwhelming burst of high-energy radiation, far beyond anything we observe. But that's not what happens. Instead, the energy rises to a peak and then gently falls off, a smooth curve, finite, well-behaved. Reality remains calm, even where the theory predicts chaos. This mismatch became known, somewhat dramatically, as the ultraviolet catastrophe. The name captures the essence of the problem, but beneath it lies something more subtle. It is not just that the theory made an incorrect prediction, it is that the underlying assumptions, the idea that light behaves purely as a wave, carrying energy in a continuous way, were no longer sufficient. The elegance of Maxwell's wave picture, as beautiful as it was, could not fully explain what was being observed, and that realization marked a turning point, because it suggested that something deeper needed to change. Not just a small adjustment, but a shift in how energy itself was understood. At this moment, the solution did not come from abandoning the wave idea entirely, but from modifying it in a very unexpected way. A scientist named Max Planck approached the problem with a kind of cautious creativity. Instead of assuming that energy could be emitted in any amount, smoothly and continuously, he proposed something unusual. What if energy comes in small discrete packets? Not an unbroken stream, but tiny steps. Little bundles of energy that cannot be divided further. You can imagine it like pouring sand instead of water. Water flows smoothly, filling any shape continuously. Sand, on the other hand, comes in grains. You can pour more or less, but always in tiny countable pieces. Planck suggested that light, when emitted by a heated object, behaves more like sand than water. Energy is not released in an unbroken flow. It's released in small, indivisible units. And when he used this idea, this simple but radical adjustment, the predictions suddenly aligned with observation. The curve that once exploded into infinity now settled into the gentle, finite shape that experiments revealed. It worked. But even Planck himself did not fully realize the depth of what he'd introduced. At first, it seemed like a mathematical trick, a way to fix a problem. But in reality, it was the beginning of something much larger. Because if energy is quantized, if it comes in discrete packets, then the wave picture of light is no longer complete. Something new has entered the story. Something that does not behave like a classical wave at all. And so, quietly, almost reluctantly, the first crack appeared in the foundation of classical physics, a small fracture, barely visible at first, but one that would soon widen into something impossible to ignore. As we move forward, we'll see how this idea of energy packets evolves, and how in the hands of another physicist it transforms into something even more surprising. Bringing us back once again to the idea that light may not be just a wave, but something far stranger. The idea that energy might come in small, indivisible packets was, at first, a quiet suggestion. It solved a problem. It brought theory back into alignment with observation, but it didn't immediately overturn the way people thought about light. Max Planck himself saw it more as a useful adjustment than a radical shift, a way to keep the broader picture intact. But as is often the case in science, an idea that begins as a small fix can grow into something much larger when viewed from a different angle. And that is exactly what happened when Albert Einstein turned his attention to light. Einstein took Planck's idea seriously in a way that others had not yet done. Instead of treating these packets of energy as a mathematical convenience, he asked a deeper question. What if these packets are real? What if light itself is not just a wave that sometimes behaves strangely, but is actually made of discrete units of energy? This was a bold step, because it meant returning in a sense to the particle idea that had once been set aside. But this time, the particles were not imagined as tiny classical objects moving through space. They were something new, quanta of light, photons. To explore this idea, Einstein focused on a phenomenon that had puzzled scientists for some time, the photoelectric effect. You can imagine it in a simple way. Take a piece of metal and shine light on its surface. Under certain conditions, the metal begins to release electrons, tiny charged components that are normally bound within the material. It's as if the light is knocking them loose. At first glance, this might seem straightforward. If light is a wave, then increasing its intensity, making it brighter, should deliver more energy to the surface, and eventually that energy should build up enough to free the electrons. But that is not what experiments showed. Instead, something far more surprising happened. The key factor was not how bright the light was, but what kind of light it was. Light of a certain colour, corresponding to a certain frequency, could release electrons immediately, even if it was very dim. But light of a lower frequency, no matter how intense, failed to release any electrons at all. You could shine a very bright red light and nothing would happen, but a faint blue or ultraviolet light could trigger the effect instantly. This behaviour was difficult to explain using the wave picture alone. If energy were delivered continuously, like water filling a container, then even low-frequency light should eventually accumulate enough energy to release electrons given enough time. But that delay never appeared. The response was immediate, or it did not happen at all. Einstein's insight was to reinterpret what was happening. Instead of thinking of light as a continuous wave delivering energy gradually, he imagined it as a stream of individual packets. Each photon carries a specific amount of energy, determined by its frequency. Higher frequency light corresponds to higher energy photons. Lower frequency light corresponds to lower energy photons. Now, imagine each photon as a tiny delivery. When a photon strikes the metal, it transfers its energy all at once. If that energy is sufficient to free an electron, the electron is released immediately. If it is not, nothing happens, no matter how many low-energy photons arrive. It's not about accumulation. It's about whether a single photon carries enough energy in that moment. You can think of it like trying to open a locked door. If each attempt requires a certain minimum force, then pushing gently many times will not open it. But a single strong push might. In this analogy, the strength of the push corresponds to the energy of a photon, and that energy depends on the frequency of the light. With this interpretation, the puzzling behaviour of the photoelectric effect suddenly made sense. Light was not just a wave, it behaved as if it were made of particles, discrete indivisible units of energy. and these particles interacted with matter in a direct, immediate way. This was a profound shift, because it did not simply modify the wave picture, it challenged it. Light, which had been so elegantly described as a wave in Maxwell's theory, now seemed to require a particle description as well. Two seemingly incompatible pictures, both necessary, both supported by experiment. And this dual nature, wave and particle, was not just a temporary confusion, it was the beginning of a new framework, a new way of understanding the physical world. Einstein's work on the photoelectric effect was so important that it later earned him the Nobel Prize. Not for relativity, as many people assume, but for revealing this particle-like aspect of light. And yet, even this was not the end of the story, because now the tension had deepened. Light behaves like a wave when it spreads and interferes. Light behaves like a particle when it interacts and delivers energy. It is not simply one or the other. And as scientists began to explore this duality more carefully, they discovered something even more surprising. It is not just that light can appear as a wave or a particle. It is that the way it behaves seems to depend on how it is observed, as if the act of looking, of measuring, plays a role in shaping what is seen. This idea, still quiet at this point, would soon grow into one of the most profound and unsettling aspects of modern physics, because it suggests that the nature of reality itself may not be entirely fixed until it is observed, and that realization begins very gently with a simple observation: a piece of metal, a beam of light, and electrons quietly leaving the surface, one photon at a time. By this point, the story of light has taken on a quiet tension. On one hand, it moves like a wave, spreading, overlapping, forming patterns that resemble ripples across a surface. On the other, it arrives like a particle, delivering energy in small, indivisible events. Both descriptions are supported by experiment. Both feel necessary, and yet placing them side by side does not resolve the mystery. It deepens it. Because now we are left with a question that feels simple, but is anything but. When a single photon travels, what is it actually doing? To explore this, we return to the same experiment we encountered earlier, a source of light, a barrier with two narrow openings, and a screen waiting quietly behind it. But this time we change something subtle. Instead of allowing many photons to pass through at once, we slow everything down, far down, until only one photon is present at a time. Imagine the scene in stillness, a dark room, a faint source of light, and then a single event. A photon leaves the source, it approaches the barrier, and then, sometime later, a tiny point appears on the screen. One dot, a brief flash, then silence again. Another photon, another dot, each event separate, independent, almost like distant footsteps echoing in an empty hall. At first, the pattern on the screen looks random, just scattered points, with no clear structure. But as time passes, something begins to emerge, slowly, almost imperceptibly. The dots begin to arrange themselves into a pattern, not two clusters, as you might expect if each photon passed through one slit or the other, but the same interference pattern we saw before, bright regions where many dots accumulate, dark regions where few or none appear. And this is where the quiet confusion begins, because each photon arrives as a single, localized event. It appears in one place, not spread out, not divided. But the pattern that emerges over time suggests that each photon somehow contributes to a wave-like interference, as if it had the access to both paths at once. If you try to picture this in familiar terms, it becomes difficult. If the photon were a particle, you would expect it to pass through one slit or the other, like a tiny traveller choosing a path. If it were a wave, you might imagine it spreading out, passing through both slits and interfering with itself. But here, we are dealing with a single photon, not many, just one. And yet, the outcome suggests that it behaves as though both possibilities are present. Not one path, not the other, but a kind of quiet coexistence of both. This idea is often described as superposition, a word that sounds technical, but can be approached gently. You can think of it as a state where multiple possibilities exist together, not as separate alternatives, but as overlapping aspects of a single situation, like a soft chord in music, where several notes blend into one sound. The photon, before it is detected, is not confined to a single, definite path. It is described by a range of possibilities, a kind of spread-out presence, where different outcomes are all, in some sense, available. And then, when the interaction happens, when the photon is detected on the screen, this range of possibilities resolves into a single event, a single point, a single outcome. It is as if the photon exists in a gentle state of maybe until it is asked a question, and then in that moment it gives a definite answer. This is already a strange idea, but it becomes even more intriguing when we ask a slightly different question. What if we try to observe which path the photon takes? What if we place a detector near the slits, designed to tell us whether the photon passed through the left opening or the right? At first, this might seem like a simple extension. We are just gathering more information, but the result is not what you might expect. When we attempt to measure the path, the interference pattern disappears. The dots on the screen no longer form the familiar bands of light and dark. Instead, they cluster into two groups, aligned with the slits, as if each photon now behaves like a particle, choosing one path or the other. The wave-like behavior fades. The particle-like behavior becomes dominant, and all we did was try to look. This is one of the first moments where the nature of observation begins to feel different, because it is not just that we are revealing what the photon was already doing. It seems that the act of measuring changes the outcome, not in a dramatic, forceful way, but in a quiet, fundamental way, as if the question we ask influences the answer we receive. If we do not ask which path the photon takes, we see a pattern that suggests it explored both. If we do ask, we find a definite path, but lose the interference. Two different behaviours, two different realities, both arising from the same underlying situation. At this point, it may be helpful not to rush toward an explanation, but to simply sit with the feeling of it. A single photon, passing through an experiment, leaving behind a pattern that suggests it was more than just a point moving along a line, a pattern that hints at something spread out, something layered, something not entirely fixed until the moment of interaction. And perhaps, in that quiet space between emission and detection, the photon is not travelling in the way we imagine at all, not following a single path, but existing as a range of possibilities, gently overlapping until the universe, in a sense, asks it to decide. As we continue, we'll explore what happens when this idea is taken even further, when the role of observation becomes more than just a detail and begins to reshape how we think about reality itself. There is a quiet moment, just after you understand the single photon experiment, where something begins to feel unsettled. Not in a dramatic way, more like a soft shift beneath your feet, as if the ground you thought was solid has become just a little less certain. Because up to this point, we've been describing light as something that behaves differently depending on how we look at it. But now, the question becomes deeper. Is the photon behaving differently? Or is reality itself unfolding differently depending on what we choose to observe? To explore this, let's return once more to the double-slit experiment. The same simple setup: a source of light, two narrow openings, and a screen. We've already seen what happens when we leave the system undisturbed. Photons arrive one by one, each as a small, localized event, and over time they build an interference pattern, a gentle arrangement of light and dark bands that suggests something wave-like happened along the way. But now we introduce a subtle change. We place a detector near the slits, not something large or disruptive, just a small device designed to answer a simple question. Which path did the photon take? Did it pass through the left slit or the right? It feels like a reasonable thing to ask. After all, in everyday life, objects follow paths. If something moves from one place to another, we expect that it travelled along a specific route, even if we didn't watch it closely, so we set up the detector. And we begin the experiment again, one photon at a time. At first, everything seems normal. A photon is emitted, it approaches the barrier, and now, as it passes through one of the slits, the detector quietly registers its presence, left or right. A clear answer, a definite path. And then, as before, the photon arrives at the screen, leaving behind a small dot. But as more and more photons arrive, something unexpected becomes visible. The interference pattern is gone. In its place, we see two clusters of dots, aligned with the slits. No alternating bands, no subtle pattern, just two groups, as if each photon simply passed through one slit or the other, like a classical particle. And this is the moment where the question deepens, because nothing about the physical setup, apart from the act of measurement, has changed. The slits are the same, the distance is the same, the photons are the same. The only difference is that now, we're asking a question, and the act of asking that question seems to change the outcome. If we do not measure the path, the photon behaves in a way that suggests it explored multiple possibilities. If we do measure the path, it behaves as if it chose a single one. This is not just a limitation of our knowledge. It is not that the photon always had a definite path, and we simply failed to detect it before. Because when we attempt to detect it, the pattern itself changes, the behavior changes, the outcome changes. It is as if the photon does not decide how to behave until the moment of interaction. And that idea introduces something subtle, but profound. Information matters, not just physical interaction, but the availability of information. Whether or not it is possible to know which path the photon took affects what we observe, even if we never look at the data, even if no one checks the result. The mere presence of a detector capable of revealing the path is enough to alter the behavior. You can think of it like this. Imagine walking through a quiet room alone. You move freely, without thinking too much about your steps, but the moment you know you are being watched, even if you cannot see the observer, you begin to move differently. Your posture changes. Your movements become more deliberate. In a very loose sense, the photon seems to respond in a similar way. When there is no possibility of knowing its path, it behaves like a wave, spread out, exploring possibilities. When there is a possibility of knowing, it behaves like a particle, localized, definite, and this leads us to something known as the measurement problem. Again, the term sounds technical, but the idea can be approached gently. Before measurement, the photon is described by a range of possibilities. Not one path, not the other, but a kind of overlap of both. After measurement, we observe a single outcome, a definite result. The transition between these two descriptions, the quiet shift from possibility to actuality, is what we call measurement. But what causes this shift? Is it the interaction with the detector? Is it the presence of information? Is it something deeper about how reality itself is structured? These questions do not have simple answers. Even today, they remain at the heart of quantum physics. But what we can say, gently and carefully, is this. The act of observation is not passive. It does not simply reveal what was already there. It plays a role in shaping what becomes real. And that idea, while subtle, changes the way we think about the world. Because it suggests that reality at its most fundamental level may not be fully defined until it is observed, not in a dramatic or mystical sense, but in a quiet, structural way, a way that reflects the deep relationship between possibility and outcome, between what could happen and what actually does. As we continue, we'll explore what happens when this idea is taken even further, when it is not just the present that seems to depend on observation, but even the past. And as strange as that may sound, we will approach it slowly, gently, allowing the ideas to unfold in their own time. By now, the story has taken on a quiet strangeness. We've seen that a photon can behave like a wave when left undisturbed, and like a particle when we try to observe its path. We've seen that simply having the ability to know something, such as which slit the photon passed through, can change the outcome of an experiment. And perhaps you have allowed that idea to settle gently in your mind. Observation matters, information matters, but what we're about to explore takes that idea one step further. Because now, we begin to ask a softer, more delicate question. What happens if we remove that information? Not before the photon travels, not before it reaches the screen, but after. To approach this, imagine the same double-slit experiment once more. A source of light, 2 slits, a screen. But this time, we include detectors near the slits, devices capable of recording which path each photon takes. So as each photon passes through, the system quietly gathers information, left or right, a definite path. And as we've seen, once this information exists, the interference pattern disappears. The screen fills with 2 clusters instead of soft overlapping bands. Everything behaves as though the photon chose a single path. Now comes the subtle twist. Before we examine the data, before we allow anyone to see which path each photon took, we introduce a new step. We erase the information, carefully, completely. As if it had never been recorded, no trace remains, no way to recover which path was taken. And then, we look at the pattern on the screen. What would you expect? If the photon had already chosen a path, if its behaviour were fixed at the moment it passed through the slits, then removing the information afterwards should make no difference. The pattern should remain as 2 clusters. The path should already be decided. But that is not what happens. Instead, the interference pattern returns. The soft bands of light and dark reappear as though the photon had once again behaved like a wave, as though it had never committed to a single path at all. This is the essence of what is often called the quantum eraser, and it invites a question that feels almost too quiet to ask. If the pattern depends on whether the information exists, even when that information is erased after the fact, then what does that say about what really happened? Did the photon go through one slit, both, or neither, in the way we usually think about it? It begins to feel as though the concept of a fixed past, of a single, definite sequence of events, is becoming less certain. Not in a dramatic sense, but in a subtle, structural way. Because here, the outcome seems to depend not only on what physically occurred, but on what can be known about it. You might imagine it like writing a story on a piece of paper. If the story is written clearly and preserved, it feels fixed. But if the words are gently erased before anyone reads them, it is as though the story never fully existed in a definite form. Not because the writing did not happen, but because it left no trace that could define it. In the quantum eraser experiment, something similar seems to unfold. The photon's behaviour, whether it appears wave-like or particle-like, depends on whether information about its path is available. And when that information is removed, even after the event, the behaviour shifts accordingly. This does not mean that the past is being rewritten in a dramatic time-travelling sense. It is something quieter than that. It suggests that certain aspects of the past are not fully determined until the conditions of observation are complete. That what we call what happened may depend in part on how the information about that event is structured and preserved, and this idea begins to soften the boundary between past and present. Because we are used to thinking of time as a sequence of fixed events. The past is settled, the present is unfolding, the future is open, but here the distinction becomes less rigid. The past in a certain sense remains open until it is fully defined by the available information. And that can feel unusual, perhaps even slightly uncomfortable, but there's also a quiet beauty in it. A sense that reality is not simply a collection of fixed points, but a gentle interplay between possibility, interaction, and knowledge. A world where what exists is not just determined by what happens, but by what can be known. And as we move forward, this idea will deepen even further, because in the next step we will encounter a situation where the choice of how to observe a photon is made after it has already passed through the slits, a situation where the future seems to reach back and influence what we think of as the past, and once again we will approach it slowly, allowing the strangeness to unfold without rushing to resolve it. There is a certain point in this journey where the ideas begin to feel less like answers and more like gentle questions that linger. We have seen that a photon does not behave in a fixed way until it is observed. We have seen that the availability of information, whether or not we could know something, can shape the outcome of an experiment. And then quietly another question emerges. What if the timing of that choice matters? Not just whether we observe, but when. To explore this, imagine once again the familiar setup. A source of light, two narrow slits, a screen waiting behind them. A photon is emitted, travels toward the barrier, and passes through the slits. Now, in earlier experiments, we decided in advance whether or not to measure its path. We either placed detectors at the slits, or we did not. But in this version, we delay that decision. We allow the photon to pass through the slits without immediately choosing how we will observe it. Only after it has already gone through, only after that moment has passed, do we decide how to measure the outcome. It feels like a small change, but the consequences are surprisingly deep. This idea is often associated with a physicist named John Archibald Wheeler, who explored what is sometimes called a delayed choice experiment. The essence of it is simple. You let the photon begin its journey without fixing the experimental conditions, and only later, after it has already encountered the slits, you choose whether to observe it in a way that reveals a particle-like path or a wave-like pattern. From an everyday perspective, this might seem straightforward. Surely the photon must have already done something by the time we make our choice. It must have either gone through one slit, or both, or followed some path that is already fixed. Our later decision should simply reveal what already happened. But when the experiment is performed, the result suggests something else. If we choose to observe the photon in a way that reveals its path, the outcome behaves as though it travelled through one slit. If we choose to observe it in a way that reveals interference, the outcome behaves as though it explored both paths. And this choice is made after the photon has already passed the slits, which raises a quiet, almost uncomfortable question. What was the photon doing before we made the choice? Did it decide in advance? Or is the outcome only determined once the full experimental setup is complete, including the choice made afterward? It begins to feel as though the photon's past behaviour is not fully defined until the moment of measurement. not in the sense that the past is being rewritten in a dramatic way, but in a more subtle sense, that the description of what happened depends on how the entire situation is arranged, including decisions made later in time. You can imagine it like reading the ending of a story before the beginning. Once you know how the story concludes, the earlier events take on a certain meaning. They seem to lead naturally to that ending, even if they felt ambiguous before. In a similar way, the delayed choice experiment suggests that the story of the photon's journey is not fully determined until the conditions of observation are complete. The past in this context is not a fixed sequence waiting to be uncovered. It is part of a larger pattern that only becomes fully defined when all the pieces are in place. This idea does not violate the basic structure of cause and effect in the way we might first imagine. There is no signal travelling backward in time, no information being sent into the past. Instead, it suggests that our classical way of thinking, where events have definite properties independent of observation, may not fully apply at this level. The photon does not carry a detailed classical history with it as it moves. It carries possibilities, and those possibilities are shaped into a definite outcome only when the conditions of measurement are complete, including choices made after certain points in its journey. This can feel difficult to hold on to, because it challenges something very deeply rooted in our intuition, the idea that the past is fixed and the future is open. Here, the distinction becomes softer. The past is not entirely independent of how we choose to observe it, and the future is not entirely separate from how the past is described. Instead, both seem to be part of a single, connected structure, a quiet unfolding of possibilities into actual events. You don't need to resolve this completely. In fact, it may be more helpful not to simply allow the idea to rest gently without forcing it into familiar shapes. Because what these experiments are revealing is not just a property of photons, they're revealing something about the framework we use to understand reality, a framework that works beautifully in everyday life, but begins to soften and shift when we look closely enough. And perhaps that is the most important takeaway. Not that the photon is behaving strangely, but that our expectations of how things should behave are being quietly stretched. As we move forward, we'll step into another aspect of this story, one that involves not just a single photon, but pairs of photons, connected in a way that seems to reach across space itself. And once again, we will approach it slowly, allowing the sense of wonder to unfold without rushing towards certainty. Up to this point, we've been following the story of a single photon, a solitary journey, moving from one place to another, revealing its strange nature through experiments that gently challenge our intuition. But now the story expands, because sometimes photons are not alone. Sometimes they are created together, in pairs. And when that happens, something remarkable begins to unfold. Imagine a single event, perhaps within a crystal or another carefully prepared system, where energy is transformed into two photons at the same moment. They emerge together like twins, moving away from each other in opposite directions. At first, this may not seem unusual. Two objects created together, then travelling apart. But what makes these photon pairs special is not just their shared origin. It is the way they remain connected, not through a visible thread, not through a signal travelling back and forth, but through a shared state, a kind of quiet relationship that persists even as they move farther and farther apart. This phenomenon is known as quantum entanglement. And although the word may sound technical, the idea can be approached gently. You can think of the two photons not as completely separate entities, but as parts of a single, extended system. Even though they occupy different locations in space, their properties are not fully independent. Instead, certain aspects of them are linked. To explore this, imagine that each photon has a property we can measure, something like a direction or orientation. We don't need to define it precisely. It's enough to think of it as a feature that can take on one of two possible outcomes when measured. Now, here is where things become interesting. Before we measure either photon, the pair exists in a state where both possibilities are present, in a kind of shared superposition. But the moment we measure one photon, we obtain a definite result, and instantly, the other photon, no matter how far away it is, takes on a corresponding result, not after a delay, not gradually, but immediately. As if the two outcomes are coordinated. If one is found in one state, the other is found in a matching or complementary state. And this correlation holds true even if the photons are separated by great distances. Across a room, across a continent, even across vast stretches of space. At first glance, this can feel as though some kind of signal must be passing between them. A message sent from one photon to the other, telling it how to behave. But careful experiments have shown that this is not what is happening. There is no exchange of information in the usual sense. Nothing travelling from one location to another, and importantly, no way to use this connection to send messages faster than light. Instead, the correlation seems to arise from the fact that the two photons were never fully separate to begin with. They are part of a single, unified description, a shared state that only reveals its structure when measurements are made. This idea was once deeply unsettling, even to the scientists who helped develop quantum theory. Albert Einstein famously referred to it as spooky action at a distance, reflecting a discomfort with the idea that distant objects could be so closely linked without any apparent connection. For many years, it was hoped that this behavior could be explained by hidden details, unknown properties carried by each photon that determine the outcome in advance. But experiments, guided by ideas such as Bell's theorem, showed that no such simple explanation could account for what was observed. The correlations between entangled photons are stronger than what any classical, predetermined model would allow. In other words, the outcomes are not decided in advance, carried quietly from the moment of creation. They are determined at the moment of measurement, in a way that reflects the shared structure of the system as a whole. This does not mean that the photons are communicating. It means that the system they belong to cannot be fully described by assigning separate independent states to each part. They are in a sense still connected, not by a signal, but by the deeper framework that defines their existence. If you imagine tearing a single sheet of paper into two pieces, you might think of them as separate objects. But if the pattern printed on the paper only makes sense when both pieces are considered together, then each piece alone does not carry the full story. Entangled photons are like fragments of a larger pattern. Individually, they appear random, but together they reveal a hidden order. And that order becomes visible only when both are measured and compared. There is something quietly profound in this, because it suggests that separation, something we take for granted in everyday life, may not be as fundamental as it seems. That at a deeper level, the universe may be woven together in ways that are not immediately visible. Connections that do not rely on distance, relationships that persist without a medium. A kind of unity beneath the surface of apparent independence. As we continue, we will gently step back and look at what this means on a larger scale, not just for pairs of photons, but for the structure of reality itself. Because if even two particles can remain connected across space, what does that say about the universe as a whole? There is a quiet shift that happens after you begin to understand entanglement. At first, it feels like a strange property of certain experiments, something unusual that appears under carefully controlled conditions involving delicate setups and isolated particles. But if you let the idea settle a little longer, it begins to expand. Because entanglement is not just about photons behaving in surprising ways, it hints at something deeper, something about how the universe itself is structured. We're used to thinking of the world as made of separate things, objects with boundaries, you and the air around you, a tree and the space between its branches, one particle here, another particle there. Distance feels meaningful, separation feels natural. If something happens in one place, we expect it to remain local, confined to that region, unless something travels from there to somewhere else. This intuition works beautifully in everyday life, but entanglement gently challenges it. Because here we have two photons that can be separated by vast distances, and yet their properties are not independent. They do not carry fully separate identities. Instead, they are described by a shared state, a single mathematical description that includes both, even when they are far apart. And when one is measured, the outcome is immediately reflected in the other. Not through a signal, not through a hidden connection travelling through space, but because, at a deeper level, the two were never fully separate to begin with. This idea is often described using the word non-locality. It suggests that the behaviour of a system cannot always be explained by looking at each part individually within its own local region. Instead, the system must be understood as a whole. Now, it is important to move gently here. Non-locality does not mean that information is travelling faster than light. It does not allow messages to be sent instantly across space. All the usual rules about communication remain intact. What changes is not how signals move, but how relationships are defined. The outcomes are correlated in a way that cannot be explained by any local mechanism. But those correlations only become visible when the results are brought together and compared. Until then, each measurement appears random on its own. You can think of it like two sealed envelopes, prepared in a special way. Each envelope contains a card, but you don't know what is written on them. When you open one envelope, you see a result, and when you later open the second, you find a matching or related result. At first, you might imagine that the cards were filled out in advance, their contents decided before the envelopes were separated. But in the case of entangled photons, experiments suggest that this is not sufficient. There is no simple set of pre-written instructions inside each envelope. The outcomes are not fully determined ahead of time, they emerge in the moment of measurement, in a way that reflects the shared structure of the system, and this is where the idea begins to broaden. Because if even simple systems, pairs of photons, can exhibit this kind of deep connection, what does that imply about the rest of the universe? It suggests that the boundaries we perceive, between objects, between locations, between events, may not be as fundamental as they appear. That separation might be, in some sense, an emergent feature, a useful way of organising experience, but not the deepest layer of reality. At a deeper level, there may be a kind of unity, a fabric of relationships, where what we call parts are really aspects of a larger whole. You might imagine it like a vast ocean. On the surface you see waves, individual shapes rising and falling, each with its own form. They appear separate, but beneath the surface they are all expressions of the same body of water. Their boundaries are temporary, their identities fluid. In a similar way, entangled systems suggest that what we perceive as separate particles may, at a deeper level, be part of a continuous structure, and that their behaviour cannot always be understood in isolation. This does not mean that everything is entangled with everything else in a simple or immediate way, but it does suggest that the framework of separateness, the idea that the world is made of independent building blocks, may be incomplete, that relationships may come first, and that objects, as we perceive them, are secondary. This shift in perspective can feel subtle, It does not change how we experience the world from moment to moment. A table still feels solid. A distance still feels real. But it invites a different way of thinking, a quieter way of understanding, one that allows for connection without direct contact, for correlation without communication, for unity without losing individuality. And perhaps, in that quiet space between separation and connection, we begin to glimpse something about the nature of reality itself, not as a collection of isolated things, but as a gently interconnected whole. As we move forward, we will take this sense of connection and turn it in another direction, not across space, but across time. Because just as photons reveal something unexpected about distance, they also reveal something equally unexpected about time itself. There is a certain quiet certainty we carry with us in everyday life. If something happens, it happens somewhere. And if it affects something else, there must be a connection between the two, a path, a signal, a movement from one place to another. We're used to thinking in terms of cause and effect, unfolding across space and time in a steady, predictable way. But as we begin to follow the story of light more closely, we find that it plays a very special role in this structure, not just as something that travels through the universe, but as something that defines the limits of how anything can travel at all. Light moves at a speed that is not simply very fast. It is, in a very real sense, the maximum speed at which any influence can propagate. Nothing, no signal, no object, no transfer of information can exceed this speed. And what is remarkable is that this speed is always the same. No matter how you move, no matter where you are, no matter how fast you yourself are travelling, the speed of light remains constant. This idea, which might feel subtle at first, carries profound implications, because if the speed of light is fixed, then space and time themselves must adjust in order to accommodate that constancy. To explore this, imagine two observers, one standing still, watching a beam of light pass by, another moving at a steady speed, also observing that same beam. In everyday experience, we might expect that the moving observer would measure the light differently, perhaps seeing it move faster or slower relative to their own motion. But that is not what happens. Both observers measure the same speed. And for that to be true, something else must change. Time itself must flow differently for each observer. Distances must adjust. Clocks tick at different rates. Lengths contract or expand slightly. Not in a way that is noticeable in daily life, but in a way that becomes significant at very high speeds. This is the essence of what we call relativity. Again, the word may sound technical, but the idea can be approached gently. Space and time are not rigid, fixed backgrounds. They are flexible. They adapt in order to preserve the consistent behaviour of light, and in doing so they form a unified structure, what we often call space-time. Instead of thinking of space and time as separate, it can be helpful to imagine them as interwoven, like threads in a fabric. Events do not just occur in space or in time, but in this combined structure, and light moves through this structure in a very particular way. It traces out paths that define the limits of what can influence what. This brings us to a concept sometimes described as the light cone. You don't need to picture it as a precise geometric shape. It's enough to imagine it as a kind of expanding boundary. If an event happens, say, a flash of light at a certain moment, then there is a region of space and time that can be affected by that event. A growing sphere of influence, expanding outward at the speed of light. Anything inside that expanding region can in principle be affected. Anything outside it cannot, at least not yet. In this way, light defines the structure of causality. It determines what can be connected by cause and effect, what events can influence each other, and what events remain forever beyond each other's reach. This is not just a detail of how light behaves, it is a fundamental feature of the universe. Because if the speed of light were different, if it were faster or slower, then the structure of space-time itself would be different. The relationships between events would change, the boundaries of influence would shift. In a sense, light is not just something moving through the universe, it is something that helps shape the universe. And the photon, as the smallest unit of light, carries this role in a very direct way. Each photon moves at this constant speed, tracing out a path through space-time that reflects these fundamental limits. It does not accelerate, it does not slow down, it simply moves, always at the same pace, always along the structure defined by space-time itself. And this leads us to a quiet realization. The photon is not just another object moving through space, it is intimately tied to the structure of space and time. Its behavior is not just governed by the rules of the universe, it helps define them. And as we follow this idea a little further, we arrive at something even more subtle. Because if space and time adjust themselves to preserve the speed of light, then what does that mean for the photon itself? How does time appear from its perspective? This is a delicate question, and as we move into it, we will do so slowly, allowing the idea to unfold without forcing it into familiar shapes. Because what we will find is that for a photon, the journey through space may not feel like a journey at all. There is a moment when thinking about light and time where the ideas begin to feel less like motion and more like stillness. Up to now, we have been describing how light moves, how it travels across space at a constant speed, how it defines the limits of cause and effect. But now, we gently turn the perspective around. Instead of asking how light moves through time, we ask something quieter. How does time unfold for light itself? To begin, let's return to something familiar: sunlight. Every morning, light from the sun reaches the earth, warming the surface, illuminating the sky, and making life possible in ways we rarely stop to consider. We know, from careful measurement, that this light takes a little over 8 minutes to arrive. If the sun were to suddenly disappear, we would not notice immediately. The sky would remain bright for those few minutes as the last of the travelling light completed its journey. From our perspective, that journey is real. It takes time, it spans distance, it unfolds step by step. But relativity invites us to look at this situation from a different angle. Not from the perspective of the Earth, not from the perspective of an observer watching the light pass by, but from the perspective of the light itself. And here, the story becomes more subtle. As objects move faster and faster, approaching the speed of light, time for those objects begins to slow down relative to an external observer. Clocks tick more slowly. Processes unfold more gradually. This is not something we notice in everyday life, because the speeds we experience are far too small for the effect to be significant. But as the speed increases, the effect becomes more pronounced. And as we approach the speed of light, something remarkable happens. Time, from that perspective, slows to a standstill. Again, we're not speaking in exact equations here, but in a gentle description of what those equations imply. For something moving at the speed of light, the passage of time along its path does not unfold in the usual way. It does not experience duration. It does not move from one moment to the next. Instead, its journey can be described as having no elapsed time at all. This does not mean that the photon has a clock that stops. In fact, it is more accurate to say that the concept of a clock does not apply in the usual way, because the photon does not have a rest frame, a perspective in which it is stationary. It is always moving at the same speed. Always. And so, from its own path through space-time, The interval between emission and absorption is 0. This can feel difficult to picture, because our intuition is built on experiences where time flows continuously. But here, we are invited to consider something different. A photon leaves the surface of the sun. It travels across millions of kilometers of space, and then it is absorbed, perhaps by your eye, or by a leaf, or by a grain of dust. From our perspective, this takes time, but from the structure of space-time along the photon's path, these two events, emission and absorption, are directly connected, without any passage of time in between. It is as if the journey is compressed, not shortened in distance, but in duration. A path through space that does not unfold in time. You might imagine it like a story that is read all at once rather than page by page, or like a bridge that connects two places without any sense of travelling across it. Not because the distance is gone, but because the experience of moving through it is absent. And this is not limited to sunlight. Consider light that has travelled across the universe. Photons that were emitted billions of years ago from distant galaxies. They have been moving through space since long before the Earth existed, carrying with them information about the early universe. When we observe that light today, we are looking into the past. We are seeing events that occurred billions of years ago. And yet, from the perspective of those photons, there has been no passage of time. The moment they were emitted and the moment they are detected are, in a sense, directly connected. This does not mean that the universe itself is timeless. From our perspective, time flows. Stars form and fade. Galaxies evolve. Life emerges and changes. But the photon moves along a path where time, as we understand it, does not accumulate. It exists along the boundary of space-time, at the edge where our usual concepts begin to soften. And this brings us back to something we touched on earlier. The photon is not just a traveller. It is part of the structure that defines how travel itself is possible. It moves along the very limits of what the universe allows, and in doing so, it reveals something subtle about the nature of time. That time is not absolute, not universal, but something that depends on motion, on perspective, on the path taken through space-time. For us, the journey of light unfolds over minutes, or years, or billions of years. But for the photon, there is only connection, emission, absorption, a single, continuous link between two events. And perhaps, in that quiet realization, we begin to see that light is not just illuminating the world around us. It is illuminating the structure of reality itself, showing us gently that space and time are not fixed stages on which events play out, but flexible, interconnected aspects of a deeper whole. As we move into the final part of our journey, we will bring these ideas together. The wave, the particle, the field, the connection across space, the stillness across time. And we will ask once more the question we began with. What is a photon really? We began with something simple, light on your skin, a glow in the dark, a quiet presence that makes the world visible without asking for attention. And step by step we followed that familiarity into something deeper, something that did not quite fit the shapes we expected. We saw that light can behave like a wave, spreading, overlapping, forming patterns like ripples on water. We saw that it can behave like a particle, arriving in small indivisible events, delivering energy in quiet, precise moments. We saw that a single photon can seem to explore multiple possibilities at once, and only settle into a definite outcome when it's observed. We saw that two photons can remain connected across space, their outcomes linked in a way that does not depend on distance. We saw that light defines the very structure of causality, shaping what can influence what. And we saw that for the photon itself, time does not unfold in the way we experience it. All of these pieces taken together begin to point toward a realization that the photon is not simply a thing, not a tiny object moving through space, not a classical particle following a path, and not a wave in the sense of a substance rising and falling. Instead, in modern physics, the photon is understood in a different way, as a ripple, a small excitation of something deeper, a disturbance in the electromagnetic field. Now, the word field can feel abstract, but we can approach it gently. Imagine a vast, invisible fabric that fills all of space, not something you can touch, but something that is always present. At every point, even in what we call empty space, this field exists, and under certain conditions it can be disturbed, it can ripple, and when it does, that ripple can travel, not because something is pushing it forward, but because the structure of the field allows the disturbance to sustain itself. That travelling ripple is what we call a photon, not a separate object, but a pattern of motion within a deeper structure. In this view, the universe is not built from tiny solid building blocks, it is built from fields, continuous underlying systems that can give rise to particles when they are excited in specific ways. A photon is one such excitation, a brief, localized pattern that appears, moves, and then disappears when it transfers its energy. And this brings us back to something we touched on earlier, the idea that a photon is less like an object and more like an event, a moment where energy is transferred from one place to another, from emission to absorption. Between those 2 points, what exists is not a tiny ball travelling along a path, but a spread of possibilities, a wave-like description that captures how the field can evolve, and then, at the moment of interaction, those possibilities resolve into a single outcome, a single event. This way of thinking allows us to hold together the different aspects we've encountered. The wave-like behaviour is not separate from the particle-like behaviour. They are different ways of describing the same underlying process. The ripple spreads like a wave. The interaction happens like a particle, and neither description on its own is complete. There's another subtle distinction that can be made here. Sometimes we speak of real photons, the ones that travel freely through space like sunlight or starlight, carrying energy across vast distances. And sometimes, in the deeper framework of quantum theory, we also speak of virtual photons. These are not directly observable. They do not travel in the same way. Instead, they appear briefly as part of interactions between charged particles. You can think of them as fleeting exchanges, momentary connections that help mediate forces, but do not exist independently in the way real photons do. They are part of the internal language of the theory, a way of describing how interactions unfold at the smallest scales. And while the details can become quite technical, the intuition can remain simple. The electromagnetic force, the force that allows charged particles to attract or repel each other, can be understood as arising from these tiny exchanges. A constant, quiet communication happening beneath the surface of what we observe. Again, not messages in the everyday sense, but structured interactions within the field. And so, the photon appears in 2 roles, as a travelling ripple, carrying energy from place to place, and as a subtle participant in interactions, helping to shape how particles influence one another. Both aspects arise from the same underlying structure, the electromagnetic field. And when we step back and look at the whole picture, something begins to feel clear, not in the sense of having a simple answer, but in the sense of seeing how the pieces fit together. The photon is not a wave, it is not a particle, it is something that gives rise to both of those descriptions, depending on how we interact with it. It is a manifestation of a deeper layer of reality, a reminder that the categories we use, wave, particle, object, are tools, useful but not absolute, and perhaps in the end that is the quiet lesson of the photon. That reality, at its most fundamental level, is not obligated to match our expectations. It does not need to fit into the shapes we find comfortable. Instead, it invites us to expand those shapes, to allow for possibilities that feel unfamiliar at first, but gradually become part of a broader understanding. And so, as this journey comes to a close, you might return to something simple, the light around you, soft, constant, unremarkable, and yet carrying within it a story that stretches across centuries of thought, a story that connects the smallest scales of existence to the vast structure of the universe, a story that reminds us gently that even the most familiar things can hold the deepest mysteries. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully wherever and whenever you may be.